Okay, so how do you actually determine the negative zero error for a micrometer screw gauge? Okay, the principles are same as that in vernier calipers, right? So over here, okay, just like how it is opposite to the situation whereby there's a positive zero error for a micrometer screw gauge. Okay, a negative zero error for micrometer screw gauge happens when the horizontal reference line on the main scale, okay, which is over here. This is the horizontal reference line on the main scale. Okay, is below, okay, the zero mark on the rotating scale, right? So this is the zero mark on the rotating scale. So the horizontal reference line on the main scale is below the zero mark on the rotating scale. Okay, so when this is below, okay, it is a situation whereby it is a negative zero error. Alright, so what is the value of the zero error? Okay, the value of the zero error will be the value on the rotating scale, which is in line with the horizontal reference line. Okay, so what you're actually looking at is actually, okay, this value here, this line over here, this marking here is the one that is in line with the horizontal, okay, reference line, right? So this value here is actually 46. Okay, so it will actually be, okay, 0.46 mm. Okay, 46 times 0.01, because each marking on the rotating scale represents 0.01 mm. So it's 46 times 0.01 is 0.46 mm. Okay, but for the negative zero error, you need to minus away 0.50 mm to this value. Okay, so you have a minus 0.50 mm, okay, being applied to this value here. So the final zero error is negative 0.04, which is a negative zero error. Okay, so if you may recall, okay, here I'll just explain to you why do we actually have this value. So vernier calipers, if you can remember, it is minus 0.10 cm, right? Okay, whereas for the micrometer screw gauge, micrometer, I just put it like that, okay, it is you minus away 0.50 mm, correct? So okay, here it is 0.50 mm because this represents, this value here is actually just what is the value of one full rotation, okay, of the thimble, right? So if I actually rotate this thimble one full round, it actually represents 0.50 mm. Okay, so one full rotation is actually, okay, because each marking is 0.01 and there are 50 markings in one full rotation, so 50 times 0.01 you get 0.50 mm. So that's one full rotation. So therefore, in the negative zero error, you're actually minusing away one full rotation. Okay, the value of one full rotation on the rotating scale. Same thing for vernier caliper, because the vernier caliper, you will notice that each division, okay, is actually on the vernier scale, okay, is 0.01 cm, right? That's each division on the vernier scale. And then on the vernier scale, it is the scale is between 0 and 10, right? So each division on the vernier scale is 0.01 cm, and there are 10 divisions, right? 0 to 10, so there are 10 divisions. So if you actually look at the vernier scale on the vernier caliper, right, because it is between, okay, 0 and 10, and then therefore there are 10 divisions, and each division represents 0.01 cm. One full vernier scale actually represents, okay, 0.10 times 0.01 is actually 0.1 cm, correct? Okay, jump this decimal forward, okay, by one digit, and you get 0.10 cm. So actually, we are also subtracting away, okay, whatever is the full value of that vernier scale, okay, when it's read to its fullest. Okay, so that's how we actually get these values, negative 0.1 cm and negative 0.50 cm. Okay, now we'll move on to the last portion, which is measurement of time. Okay, so this is it is more experimental in nature. Okay, so the nature of the questions are such that the examiner will give you sort of like usually this will be the long structured question, okay, and there will be some instructions given to you about an experiment that's conducted, and they will draw some diagrams for you, and you will need to understand that this is an experiment, hypothetical experiment that's conducted, and you need to use those values that are given to you and make some calculations and draw some conclusions. So usually how do you measure time? You use a stopwatch, okay, and the error that usually comes into play is random error, which is a human reaction time of about 0.2 seconds, can be up to 0.3 seconds, okay. So usually the experiment will take the form of how do you measure the period of a pendulum, okay. So this green ball here with the line, okay, attached to usually is a retort stand, okay, is called a pendulum, a swinging pendulum, okay. So what is a period of a pendulum? The period is basically the time taken for this bob. So this ball here is called a bob, okay, to complete one oscillation. Okay, one period is basically, okay, so period is a measurement of time, okay, the time to complete one oscillation. Okay, so that's the definition of a period. What is one oscillation? Basically, if this position A, it goes from A to B and back to A again, right? So that is one oscillation, from A to B and back to A again. Okay, that's one oscillation. So the steps will be to you tie the pendulum bob, okay, tie at one end and you clamp it to the arm of a retort stand, pull it to one side at a certain angle, okay, which is called the amplitude, right? So this is the amplitude. Let's say if this is the bob, I pull it to one end, okay, from here I pull it to here, okay, this will be the amplitude, okay, as denoted by this S over here, okay, so this will be the amplitude, okay, of which I have displaced the bob, okay, and then I release it, and then it will start to oscillate. Alright, so this at its maximum points, okay, they have the maximum displacement, okay. So what I'll do then in this experiment is usually I will have to record the time taken to complete a certain number of oscillations, right? So I will start my stopwatch, okay, and I will count, okay, when there's one oscillation I will say, okay, there's one, and then it goes second time, there's two oscillation, three oscillation, four oscillation, okay, and usually how the number of oscillations that I will record will be 20 oscillations, okay, and then I will stop the stopwatch when it reaches 20 oscillations, and the time that's indicated on the stopwatch is the time taken, the total time taken to complete 20 oscillations, right? So the formula will be, I take this time here, okay, let's say if the total time recorded on my stopwatch is 125.6 cm, okay, is used to complete 20 oscillations. So each oscillation will just simply be, I take this time, divide by 20, okay, because this is the time for 20 oscillations, so one oscillation will be this 125.6 divided by 20, I will get 6.28 seconds is one oscillation, right? So it's just, in terms of formula, it's just total time divided by number of oscillations. Okay, so total time divided by, okay, in this case 125.6 total time, okay, divide by number of oscillations, which is 20, I'll get the period of the pendulum, 6.28. Alright. So what's the purpose of taking 20 oscillations instead of just a single oscillation? Right? Why do I have to go to the trouble of recording 20 of them? Do I have nothing better to do? Okay. No. Okay. It's because by just like how I explained previously, how do you minimize a random error? Okay. If you take 20 oscillations and you divide it by 20 to get one oscillation, okay, that random error, okay, caused by human reaction time, you are actually also dividing it by 20. Okay, so what happens is that it's averaged out and minimized. Okay, and how it helps is improves the accuracy of the experiment. Okay, so the same random error of let's say 0.2 or 0.3 seconds, I will also be dividing it by 20. Okay, when I do the calculations over here. Okay, and therefore the error will be minimized by 20 times. Okay. So this is just a formula, okay, which is how do you actually calculate period. So T represents period, okay, pi is just 3.14, okay, it's a standard value. L represents the length of the thread, Okay, over here, this is the length of the thread. Okay, important in the calculation. Okay, so and G is gravitational field strength, which is 10. Okay, so using this formula here, you can actually derive the period of the oscillation. Okay, so what you see is that actually only because G is a constant. Okay, so G is a constant. 2 pi is also a constant. So the only thing that affects the period, T is the period, is the length of the bob. Okay, so the factors that affect period will just simply be the length of the thread. So I mean not the length of the bob, the length of the thread. Okay, so usually because it's direct proportion, okay, the longer the thread, the greater the period. Okay, it's a direct proportion. And of course gravitational field strength, because G is over here, but on Earth it's just 10. Okay, so usually it's just the length of the thread that will affect it. And you will also note that, okay, the mass is not present in the equation. Right, so if I use a heavier bob and a lighter bob, it doesn't have any influence or effect on the period of the oscillation. And the amplitude, okay, amplitude will basically be, if you recall, is this over here. This is the amplitude. Okay, amplitude does not affect the period as well. Okay, because it doesn't appear in this equation, right? So these two factors, although intuitively you may think they will actually affect the period, but no, in terms of physics, okay, if you look at the formula, they actually do not affect the period of the pendulum at all. Okay, yeah. So that's all for this topic. Thank you for listening.